Swayam Prabha. Digital India. Educated India.
So first of all, I'd like to thank the organizers for having me here. It's my first time in India. I'm very excited, in particular about the friendliness of everyone, and so this is a real experience for me. And also, it is a particular pleasure that it is sort of the birthday party of Professor Satyamurthy, and we never worked together, but I sort of heard of your work already from very early on through my mentors and colleagues. Jörn Manz in Berlin, for instance, Lutz Zülicke in Potsdam, whose successor I am. And finally, we also did for a while work both on photodesorption, and this is another connection between the two of us, I think. Okay, so today I will be speaking about light-driven processes in molecules, from photophysics to photochemistry. Photophysics means that we don't break or make bonds by photons, but rather shake bonds. So for spectroscopy, for instance, or for intersystem crossing events and things like that. Whereas photochemistry, there we really do photochemical reactions. I should like to thank a few co-workers first, before I forget. This is in particular Paul Albrecht, Florian Bedurke, Tilman Klamroth, to name just a few. So all of you probably know Jablonski diagrams. So they summarize photophysics, so to say, in molecular systems. We have a ground state S0, say. We have excited states S1, S2, which we can excite by photons. And then we may have some non-reactive processes like intersystem crossing to triplet states, or internal conversion by non-adiabatic couplings between the different singlet states. All of those processes are characterized by certain timescales, which are listed here, but of course this is more a ballpark number and less so something which can be understood on a simple basis, and you really have to do some dynamics calculations to get the specific time constants out. The Jablonski diagram shows only states. In reality, we have potential energy surfaces which change their energy along some coordinates, because you have conical intersections and things like that, which then act as funnels, transition states, so to say, for photochemical reactions. And we are interested in mechanisms and also, again, in timescales of such photo reactions. The talk is divided in three parts. I don't know how far I will get, so let's start. The first one is a typical photophysical problem, and it starts from very elementary things, namely from what electrons are doing once a photon hits a molecule. And a specific application today is high harmonic generation. The second example is then already really related to photochemistry of real molecules. In particular, I will be speaking about photoisomerization of molecules in constrained environments. And the third one is a topic we became interested in more recently. I sometimes call this photochemistry without light, because we have photons, but not propagating photons. So we have electrical fields in a cavity in which molecules are placed. And this has some effect on the spectroscopy, that is the photophysics, but also on the perhaps reaction dynamics, as we shall see. So let me start with the first topic. So this is electron dynamics driven by photons in molecular systems. And what we do in our group is quantum dynamics, mostly. And one way to do so is to solve time-dependent electronic Schrödinger equations in this case. So we have the usual electronic Hamiltonian for an n-electron system. But then in addition, we have some laser field which couples through the dipole operator mu to an external electrical field E of t. And there are various ways to solve this time-dependent Schrödinger equation. Nowadays, most people would do what is called real-time time-dependent DFT. But there are other approaches as well. So, for instance, one electron approaches where one electron moves in an effective field of the molecule. Then the next stage would be the single determinant methods. And among these are the just mentioned real-time time-dependent DFT methods. You could also do time-dependent Hartree-Fock with this. A real-time time-dependent DFT is a great method, of course, but also has some disadvantages, the usual ones. So if you have, for instance, charge transfer excitations, that usually works not so well with the current functionals available. If you want to treat photochemistry or if you are close to conical intersections, for example, you may have problems. But they do work well for the standard valence excitations n pi star, pi star of an organic molecule, for example. So in order to overcome these problems, we in Potsdam developed since many years methods which are based on wave function theory, so post-Hartree-Fock methods, but time-dependent. And one of them is a time-dependent configuration interaction method, where we not only use one slated determinant, the ground state slated determinant, but we also have single, double excitations, and so forth. And in time-dependent CI, the coefficients to these determinants are time-dependent. The determinants themselves are time-independent and calculated once at the beginning before the laser pulse comes in. The more correct way in some sense would be to also account for the time dependence of determinants, that is, for the time dependence of the orbitals within the determinants. This sometimes is called multi-configurational time-dependent Hartree-Fock method, or I would rather call it time-dependent CAS-SCF method, because typically you define an active space and you include some of these excitations and freezing core electrons and not considering some of the unoccupied orbitals. So these methods are available, and we mostly work with a time-dependent CI method nowadays. And one example where we applied this method to was high harmonic generation, which is sketched here for the example of a helium atom. So here you have a laser field, an oscillator laser field in yellow coming in, and this distorts the potential which the two electrons of the helium atom see. And when the laser field changes sign, then you have a reorientation of the potential, and associated with this reorientation is a motion of the electron, one of the electrons which moves further out, then comes in again, and by coming in and recombining with the rest molecule, then you emit photons, and these are the high harmonics. And they are multiples of the incoming frequency laser pulse, so this is a way to construct high frequency radiation, which in turn can be used to make very short laser pulses, attosecond laser pulses, for example, by linearly combining these high frequency laser emission fields. So here's a very simple pedagogical example. It's a H2 molecule, and here we have the ground state, and here we have some excited states, a dark state. Here's the first bright state, which is round about 12 electron volts higher than the ground state. And we come in with a laser pulse, which excites these molecules, and our goal was to excite it from here to here, just to test the DCI method. And what we apply is a so-called pi pulse. A pi pulse is a pulse which by construction in a two-level system in the rotating wave approximation makes a population inversion. Here we have not the rotating wave approximation, we have a real molecule, But still we can use this pi pulse model in order to try to get from here to here. And what we use is a cosine function for the laser field with a certain frequency. This is just resonant with this transition. Then we have a shape function. You could use a Gaussian. We use sine square functions which have a certain width, sigma. And we have a prefactor which is determined from this pi pulse condition. And if we use a pi pulse with a certain length of 1000 atomic units, this is 25 femtoseconds, then in fact we get a full excitation from here to here by 100%. Here you see populations in the different excited states after the pulse is over, and one sees the population is 1. When we apply this laser pulse, here's the laser pulse, now here's the laser pulse, here we have the dipole moment, laser pulse, and here we have the combination of the two with the so-called Kennlinie. I think the word Kennlinie, which is a German word, is also used in the English literature here. What happens if we use a shorter pulse, in this case 50 atomic units? So this is a little bit more than a femtosecond. Then you don't create a state-to-state transition, you create a wave packet instead. In this case, it is a linear combination of two excited states, more or less 50 to 50, and the wave packet has the property that even if the pulse is over, it has some dynamics, and the dynamics, for instance, leads to an oscillating dipole moment. Now, back to the high harmonic generation. We then used this technique to calculate the response of a molecule on a non-resonant laser pulse. In this case, we used an 800 nanometer laser pulse. The molecule is also not H2 anymore, it's H2 plus to make things even simpler. And here you see a lot of different curves. These are high harmonic spectra for 3 different intensities. So we have increasing prefactors in these laser pulses which we used with increasing intensities. And you always see 2 curves. One is where we really fixed the nuclei at their equilibrium position. And the red curve is always when we allowed for nuclear motion as well. Not only electrons are moving, but also the nuclear motion is taken into account, and it is taken fully quantum mechanically into account. That is, we don't work with states anymore, but with potential energy curves and with non-adiabatic couplings between the potential energy curves. So let me start with this black curve down here. This is a typical high harmonic spectrum when the molecular distances are fixed. And you have here a decay of the signals. For instance, here you see the first harmonic, which has the frequency of the exciting laser pulse. Then we see the third, fifth, seventh, and so forth. For symmetry reasons, in this case, we only see the odd high harmonics. Yeah, and then you get to a so-called plateau region, and then there's a so-called cut-off region. This is always a typical behavior of these spectra. So as I said, in this particular work, which is relatively recent, we were interested in a nuclear motion. Does it have an effect on high harmonic spectra? Because in molecules, this effect is usually neglected. And in fact, if you go to the red curve, one sees there is quite some effect of nuclear motion. So our suggestion is that if you can afford it, try to also include nuclear motion here. This is now for a situation where the laser pulse was relatively short, 27 femtoseconds. And if you go to even longer pulses, in this case 270 femtoseconds, corresponding to 100 optical cycles. The previous example was 10 optical cycles. And then you see other interesting effects of nuclear motion. You see, for instance, vibrational sidebands in the harmonic spectra. So this is harmonic number 1. And these are curves for 3 different isotopomers of H2 in this case. H2, D2, and T2. And you see these little side peaks, and these are vibrational side bends, and they show up when the laser pulses are long. And you also may notice that you see strong isotope effects, which you would not see if you would not take the nuclear motion into account. Well, these methods are not restricted to such small molecules. In fact, we studied some years ago also bigger molecules, organic molecules, even much bigger than those shown here. I mean, this is not the end of the story, and you can calculate then high harmonic spectra for different isomers of organic molecules, for example. And you can not only do it in an energy-resolved fashion, as I just did, you can also do this in a time-resolved fashion and really see differences between different isomers. And we suggest that this technique, high harmonic generation, can also be used to distinguish organic isomers, for example, an idea which has not been exploited so far as I know. Okay, second part of the talk has to do more with photochemistry. So now we really want to break bonds, or at least change them quite a bit. And the example is the isomerization of a molecular switch, trans-azobenzene, from this form to this form, which is cis-azobenzene. Both molecules have very different properties. This one has no dipole moment, this one has a strong dipole moment. So this one is hydrophilic, this one is hydrophobic, and so forth. And people want to switch these molecules, and ideally also switch them back, either by a light, again, as the original trans to cis switching happens, or by applying heat. And they would rather also like to have these molecules not only in solutions, but they want to mount them on surfaces in order to make them useful for devices, for example. In order to describe the switching process, we use something which you probably all know. This is Tully surface hopping. So in this case, we really want to let all the atoms move, and that we cannot afford fully quantum mechanically. And therefore we treat them classically, but we allow for transitions between the various excited states. So for instance, in the case of azobenzene, we start from this trans minimum, which is lower in energy than the cis minimum. We excite to some excited state. This is a pi star excitation to a higher pi star excited state. And then the whole system starts to move, and every now and then transitions to other potential energy surfaces occur with some probability given by the non-adiabatic coupling vectors. And in the end, you may or you may not end up in the cis form. So we applied this method first, as many others did, to the pure single molecule. And here we have the molecule with some geometric parameters. For instance, there is a dihedral angle omega, which connects this C atom, this N atom, this N atom, and this C atom. And if omega is 180 degrees, the molecule is in the trans form. And if it is in round about 0 degrees, it is in the cis form. So here we have the excitation of the molecule initially. Then the red curve gives this angle omega. Initially, the angle is 180 degrees, so the molecule is still in the cis form. But then, if you look at the populations of the different excited states, you see at some point the molecule de-excites to the S1 state, which is an n pi star excitation, and there a switching occurs to the cis form. Then you have to run these trajectories for 100 times or even longer, and you can make statistics, and you find then in the end that roughly 20% of the molecules have switched from the trans to the cis form when we initially excite this pi star excitation. Now people have brought these molecules on surfaces, and they found they didn't switch anymore. And we studied this process then theoretically by considering an arrangement, a two-dimensional arrangement of such molecules. And part of the system was treated quantum mechanically from the viewpoint of the electronic structure theory. And another part was treated by molecular mechanics. So we have the QMMM surface hopping scheme applied to this particular system. And in fact, one finds that when the packing density is relatively high, like in many experiments, then the switching probability from trans to cis is very low. And if you go to a very diluted situation where the average distance between the switching molecules is sufficiently large, then the switching probability approaches that of the monomer again. And so also experiments have then confirmed this, that there is a critical packing density beyond which the switching does not happen anymore. Maybe very briefly, another thing which we looked at with the surface hopping methods was fragmentation reactions. I know that Professor Satyamurthy is also very much interested in photodissociation. And what people do when they record mass spectra of molecules, for example, they just destroy them by electronic excitation. And you can then get mass spectra, different fragments of the molecule, and these fragments also appear at different excitation energies. So in fact, one could also then plot and measure time three-dimensional mass spectra, which depend on excitation energy and the fragment. And so with this we have applied to several molecules. We also have calculated such three-dimensional mass spectra for certain molecules. But here I just want to tell you again the story for azobenzene. In azobenzene we have this trans form, but we also have the cis form. And the question we were interested in, do they have different fragmentation patterns? And in fact, they have slightly different fragmentation patterns, which is sort of surprising because the energy difference between trans and cis in the ground state is very low, low compared to the excitation energy, but still you see some differences for trans and for cis in the case of azobenzene molecules. So let me come to the last example I wanted to show you. This is photochemistry, perhaps without photons, of molecules in a cavity. A cavity can be realized in different ways. A simple one is simply that one takes two mirrors, silver mirrors or whatever, and puts a molecule inside, usually in solution. And what happens then is quite interesting. Well, you get, first of all, effects on spectroscopy. The mirror, I should say, supports electromagnetic fields, standing waves, if you want. And these electromagnetic fields, this quantized electromagnetic field, can couple to the vibrations of the molecule or to the electronic excitations. Considering the vibrational situation, here we have a sketch taken from a publication of Epperson, who is one of the pioneers in this field. So here we have a potential energy curve for a diatomic molecule, say, with the various vibrational levels. And if you couple such a quantized electromagnetic field of the cavity to the molecule, the cavity being described actually simply by an harmonic oscillator, then you get a splitting of the vibrational states in the molecule, and you get these lower and upper polariton you may have heard of. And the energy difference between the two is called the Rabi splitting. And in fact, in an infrared spectra, you not only see one line for the transition from 0 to 1, you see now two lines corresponding to the lower and the upper polaritonic state. What also has been suggested, in particular by Epperson, was that not only spectroscopy, so photophysics, would be affected by the cavity modes, but also reactivity. So he gave an example of this molecule where he claims that he can selectively break either the carbon-silicon bond or he can break selectively the oxygen-silicon bond. So you would have a tool to do mode-selective chemistry, perhaps. And so we treat these processes using a quantum electrodynamical extension of the normal Hamiltonian for a vibrating molecule, for example. This is called the Pauli-Fierz Hamiltonian. It consists of the system part, so this is just a Morse oscillator of a diatomic molecule, say. And then we have the cavity part, which is a harmonic oscillator. And then we have a coupling term, which couples the dipole moment of the molecule to the quantized field of this and there's a so-called dipole self-energy term. So the chairman stood up already. Let me just give you a very brief example. Here we have an ammonia molecule characterized by a double well potential corresponding to the H3 down and H3 up configurations. And if you add this cavity, then perpendicular to it, you also have this harmonic mode. So instead of a one-dimensional potential curve, you would now have a two-dimensional potential energy surface. And when you switch on this coupling constant from 0 to some finite value, you get a distorted two-dimensional potential energy surface for which you can do spectroscopy or you can do reaction dynamics. We have done both. And as the stairman stood up, I should just say that we did compute spectra. We also did some reaction control for hydrogen transfer of the molecule in a cavity. And I should close the fact to make the turn to the beginning again. We also placed the molecule H2 into a cavity and calculated the high harmonic spectra from this. And the result is that the cutoff energy is shifted to lower energy quite a bit when you switch on off the molecule to this cavity. So it's time to summarize. 3 topics, too many as usual. Light-driven electronic dynamics was the first one, light-driven nuclear dynamics for this switching process, and then I also talked a little bit about this cavity-induced chemistry and spectroscopy. And I would like to thank my group, my funding agency, and in particular you for your kind attention. Thank you very much.
Swayam Prabha, Digital India, Educated India.